Alright guys, I'm here to give you the problem session number 5 that we decided I was just going to present as a video, and then you guys can watch this at your leisure. And of course I've put the solutions to these problems also on the internet, so you can decide how you want to play this, if you want to try them on your own a little bit and then possibly watch the video and so on and so forth. That would be great. So these are some good problems that are related to the mean value theorem, a little bit of uniform continuity, some of the applications of derivatives, that kind of thing that we've been talking about in the last few lectures. So just going to present a few examples here for us to look at. So the first one is a really quite an important example, because you'll remember in class one of our results about derivatives was that if a function has a bounded derivative, right, so the absolute value of f prime of x is bounded, then the function is uniformly continuous on whatever domain that derivative was bounded on. So this example is going to show us that the converse of that result is not true. Okay, namely, that it is possible for a function to be uniformly continuous even though it doesn't have a bounded derivative. Now it turns out that if the domain is some finite interval from a to b, then it will be true that a uniformly continuous function will have a bounded derivative on I. But as you'll see in this example, I'm going to take I to be an unbounded interval. Okay, so if we have an unbounded domain, then it is possible to give this counterexample to the converse of that result that I just mentioned. Okay, so we're going to use the square root of x function, and we're going to show that that is uniformly continuous on I, and then we're going to show that it does not have a bounded derivative on I. Okay? In fact, it's easiest to show first that it doesn't have a bounded derivative. Let's just take a look at that. If you look at, so we'll just do this easy part first. If you just look at the derivative of the square root of x, okay, of course we can just use the power rule for this. We're going to get 1 over the square root of x. And on this domain, which consists of the positive real numbers, I can make this derivative as large of a value as I want by choosing x close to 0. Okay, so I'm just going to say which is not bounded on 0 infinity. For example, you could create a sequence xn that's 1 over n. That's certainly in the domain from 0 to infinity. But f prime of xn then would be 1 over 2 times the square root of this, which is, 2 over the square root of n then. So we just get the square root of n over 2, which is not bounded at all. Okay, so you can make arbitrarily large values for the derivative of f by just choosing inputs that are very, very close to 0. Okay, so the derivative, as we just calculated here, is not bounded on 0 to infinity. However, I'm going to go ahead and erase this. You can rewind me if you need to see this in more detail. If we look at the uniform continuity part of it, okay, of course, we usually would start out with our scratch work. Remember, we're going to take 2 points, x and y, that are both in I, right? And we want, in our scratch work, we would want to have the absolute value of f of x minus f of y less than some given epsilon, right? Okay. What we can do here, whenever we have a proof of uniform continuity, you've seen some examples of this before. X and y are kind of on an equal footing with each other. Neither one of those points is really fixed. They're just 2 arbitrary points somewhere in I. So what we can do is we can assume, so we may assume that x is greater than or equal to y. So you actually can always do this for uniform continuity on some domain. Take 2 elements in that domain. You can always just assume that the first one is greater than or equal to the second one. Okay? And in so doing, then here, of course, you're going to have square root of x minus square root of y less than epsilon, and you don't actually need absolute value bars anymore. Okay, so that's really the point of that. Assuming that we start from here, we'll put this into the proof at the very beginning that x is greater than or equal to y, and then we'll be able to reverse from here to here. Right. Okay. Now, you know, this is a little tricky. What you might be thinking of doing here is conjugating this by the square root of x plus the square root of y in order to get something that would look like this. Okay, this should look like this, less than epsilon. And so then x minus y, which is the same as the absolute value of x minus y, would be less than epsilon times the square root of x plus the square root of y. The problem is that on this domain I, right, this square root of x plus square root of y, it could be anything from arbitrarily close to 0 all the way up to infinity, right? So we're having a difficulty here in getting a delta, right? Delta is supposed to be only in terms of epsilon, and here we see that it's going to depend on x and y pretty heavily as well. So this doesn't quite work, but there is something that will work, and that is we can do a backwards arrow, which is what we need to be able to do. And what we can do is we can replace radical x minus radical y with just radical x minus y. Okay, so in other words, I claim actually, so this is coming from the claim that the square root of x minus the square root of y is less than or equal to the square root of x minus y. If you believe this claim, then you can go backwards here. Because if the square root of x minus y, which is the larger thing, happens to be less than epsilon, then surely the smaller thing is also less than epsilon. Okay, to prove this one, what you would want to do is square both sides. All right, so you would have, you know, x minus 2 radical xy plus y less than or equal to x minus y. If you just square both sides of this claim, right? And, of course, everything is positive, by the way, because, again, x is greater than or equal to y. And now if you just cancel the x's, and what we can do is we can put 2y on the left side and 2 radical xy on the right side. So this is just algebra, okay? Canceling the 2's, and then if you just simply divide the square root of y over, you're going to get something like this. The square root of y less than or equal to the square root of x. Well, that is true, because x is greater than or equal to y, so the square root of x will be greater than or equal to the square root of y as well. Okay, so you can actually justify this claim through these algebraic steps right here. Okay, so that's an algebraic manipulation, essentially. Okay? So now what you can do is you can go ahead and solve for x minus y by squaring both sides. And now you see what you want your delta to be. Okay? So let's try and run the proof now. We're going to let delta equal epsilon squared. Okay? So I'm going to erase this little part right here. Okay? Let me just see if I can put it in here and keep the scratch work on the board right there. So, you know, let epsilon greater than 0 be given, and delta equal to epsilon squared. Let's just try that. Okay? And now we're going to assume that x and y are in my domain I with x greater than or equal to y. All right? So we'll start off that way. Okay? Those are the assumptions that we had made earlier. And we're also going to assume that x minus y is less than delta. Again, normally we have absolute value bars here, but in this case I don't need them because I'm assuming that x is greater than or equal to y. Great. Okay, well then, if we have that, then x minus y is, of course, I can replace the delta with epsilon squared, and that puts us right here, and now we can retrace the scratch work. Okay, so retrace the scratch from here to get what we want, which is that absolute fx minus absolute fx minus fy is less than epsilon. Okay? So that's the proof. So the square root of x is uniformly continuous, but does not have a bounded derivative. Okay? That's the point. All right, so that's the first example. Again, if you have questions about any of the parts of the solution that I'm putting together here, by all means, just let me know. This one was a little tricky, just to that little step with comparing these two things, right? You may not have thought that we were going to need to look at that, but it turns out that that was the key to getting our delta figured out in the first place. Okay, great. All right, let's take a look at the next problem on the review sheet here. Number 2. They give you a polynomial. I'm just going to abbreviate the question here because you have the full statement of it in the handout. Here is the polynomial that they give you. All right, x to the 4th plus 7x cubed minus 9. Show that f has exactly 2 distinct real roots. Okay? Now, this might make you think of something like the location of roots, okay? And we've done this before, where you're kind of using an application of the intermediate value theorem. So you might plug in some x's, and so for example, I always like to put in 0 because that's really easy. So f of 0, for example, is negative, right? But on the other hand, if you plug in something like f of 2, right, well now, I don't even know, this is what, 16 plus 56 is 72, minus 9 would be 63. That would be greater than 0. Okay, so there has to be a root in between 0 and 2. Remember that f is differentiable on R. I should have re-emphasized that. It's differentiable on R, which means it's continuous on R. Remember that one of our early theorems in Chapter 5 was that differentiable functions are always continuous. Okay, so because of that, we can apply the intermediate value theorem here, the location of roots as a special case. Okay, and then likewise, I can pick, let's try -2, another value of x. So this would give me 16, actually that's maybe that isn't going to work, is it? We need probably a much larger number. How about -10? Okay, let's try -10. So to the 4th power, that's 10,000. And here we would be subtracting 7,000. So that gives me 3,000. And you subtract 9 from that, you're going to get 2,991. Well, that's obviously greater than 0. Okay? So by location of roots, there exists a C1 in the interval from -10 to 0 with f of C1 equal to 0. And there exists another root, C2. This one would be in the interval from 0 to 2, right? With f of C2 equal to 0. So this gives us two distinct real roots. The challenge here, the reason that I'm asking this question now, and I didn't ask you this question a week or 2 ago, is that we want to show that there are no other roots besides those two. Okay, we want to show that there can't be more than 2 roots. Okay, so imagine that there's 3 real roots or more. Okay, so suppose f has at least 3 real roots. Well, it turns out f cannot have exactly 3 real roots. This is a theorem a little outside the scope of what I've actually talked about in class. But if f had exactly 3 real roots, what you're going to notice, and I should say distinct real roots, real distinct roots, this is a 4th degree polynomial. So if you think about it, a 4th degree polynomial has to have 4 roots, including repeats and so on and so forth. So if you had exactly 3 distinct real roots, okay, you'd have a little bit of a problem with how you get just a 4th root. Because if there are complex roots that show up here, they always come in pairs. They would always have to come in pairs. So let's just think about how this would look. So I claim f cannot have exactly 3 real roots, 3 distinct real roots, because if it did, then there would have to be a 4th real distinct root. You can't have one complex number as a root. Okay, so I'm just going to make that as a note. Since complex roots of f of x must occur in pairs, they always come in conjugate pairs like that, right? F cannot have exactly 3 distinct real roots. Okay, can't have that. Okay, so there would have to be a 4th root. Okay, there would have to be 4 roots. So could f have 4 real roots, 4 distinct real roots? So say f has 4 distinct real roots. We'll call them C1 less than C2 less than C3 less than C4. Let's say we have 4 real roots like that. Okay. So in other words, the graph crosses the x-axis, whatever this graph looks like would cross the x-axis, 4 times like that. Okay. Well, this is where you can think about the derivative a little bit. Okay, so the trick to this is to look at the derivative. If you look at the derivative of a function that has 4 real roots, okay, what is the derivative here? The derivative is 4x cubed plus 21x squared, right? And if you factor that, you get x squared times 4x plus 21, right? And so the derivative is only 0. The derivative is only 0, so if we set this equal to 0, we find that x is 0 or x is negative 21/4. You can't have 3 different places where the derivative is 0. Okay, so that's really the reason that f cannot have 4 real roots. Okay, so in other words, by the mean value theorem, that's really, well, actually it's by Rolle's theorem. If you want to be really taking the simplest theorem, by Rolle's theorem, if we have these 4 distinct real roots, then there would exist, let's say, an R1 in the open interval C1, C2, and an R2 in the open interval C2, C3, and an R3 in the open interval C3, C4. Okay, so there would exist all of these with f prime of R1 equal to f prime of R2, right, equal to f prime of R3 equal to 0. These would all be then just 0. Okay, and that is where the contradiction comes in, because looking at the actual derivative of f, we see that no, there are not 3 distinct roots. These would all be distinct because they're in different intervals. There are not 3 distinct roots where the derivative is 0. Okay, so this is a contradiction. Okay, so that's kind of the idea behind that. Okay, that's how that would play out. Okay, great. I'm going to shut off the camera for a moment and restart it to do the next problem. Okay? Hope these are making sense so far.